part C of this problem is the one that'll come across as the most unusual or the biggest curveball. Notice that it is actually worth relatively few points. If you compare part B and part A, they are each worth 15 points, whereas part C is worth 10 points, and parts A and B are more similar to what you would have seen on homework. So that will hopefully reduce your stress a little bit. The other comment I want to make is that just because a problem has a curveball or is unusual doesn't necessarily mean it's hard. So while you may not want to initially focus on problems like this, you may want to go to other parts of the exam, at least I would. I do encourage you to try these problems. So let's try to figure out what's happening here. Okay, so I have a plug flow reactor just like in part A. The input is the same. A does go to B, that's the same. But now the catalyst is the reactor is filled with catalyst particles. And this bullet point explains that the effective cross-sectional area A sub C is not just the cross-sectional area of the tube because of all the particles. It's actually the sum of the void spaces in between the catalyst particles. But it doesn't matter so much here because it's just a variable. We're doing this problem purely analytically. The reaction kinetics have changed. So now A goes to A star. A star is stuck to the catalyst surface, so it actually does not flow with the fluid, but we should still treat it using basic mass action formulas. Again, that's not totally accurate in reality, but I'll let your kinetics professor go into more detail in future classes. So now A star converts to B star, which is still stuck to the catalyst surface. And as the last step, B star goes to B, and that is released in the flow. What are we actually trying to solve? We're trying to solve for the concentration of A as a function of X at steady state. So again, the hint here is remember that A star and B star do not flow. Since the problem is asking about compound A, let's do a balance on A. Remember, our control volume is between X and X plus delta X. Okay, so the input is going to be FCA delta T at X. The output, hold on, let me write the whole balance formula. In minus out plus generation minus consumption equals accumulation, which is 0 at steady state. So the output is going to be FCA evaluated X plus delta X times delta T. The generation is going to be K inverse, okay, negative 1, CA star, AC delta X delta T. AC delta X is the volume of my control volume. K minus 1 CA is the rate constant generation of A per unit volume per unit time. The consumption of A is going to be K1 CA AC delta X delta T. So we need to divide through by delta X, and I'm going to move these terms to the other side and then flip. Well, I'm going to play with negative signs. So I'm going to say limit as delta X goes to 0, CA at X plus delta X minus CA at X divided by delta X, which is dCA dx is going to equal K negative 1 CA star AC minus K1 CA AC divided by F. Okay, so now this is a differential equation for CA. I'm going to just put a box around it and label it equation 1. Notice it's not sufficient because it's asking, or it's depending on CA star, which is going to depend on X. So here's where the twist comes in. So actually, I should have mentioned this. This is exactly the same. When we did the balance on A, it's exactly the same as the balance we did in part A. So you could have just stated that, so you can refer to the equations used in part A, you could have just referred to that and said that the A balance is the same. A star, however, is going to look different. So the input is actually going to be 0 because the fluid is not capable of carrying A star into the control volume because A star is stuck to the catalyst, which isn't moving. So we're going to have 0. The output is 0. The generation term is going to be K1 CA AC delta X, and there's other terms here. I'm just looking at the kinetics. The consumption is going to have two terms, minus K inverse CA AC delta X. And you're going to consume A star by converting it minus K2 CA star. By the way, this should have been CA star AC delta X. Yeah, okay, so you don't have to balance B star. And this is actually going to equal 0. So this may make you a little uncomfortable, but this is a totally valid equation. It is not something that I can turn into a differential equation, but it's still an equation. So what I can do here is I can solve for CA star. So CA star equals, I'm going to say K1 CA AC, the delta X's are all going to cancel, divided by K negative 1 CA, oops, no, that's wrong, K negative 1 AC minus K2 AC. I think I've got the signs right. And the AC is actually going to cancel. So this actually will equal K1 over K minus 1 minus K2. Whoops, actually, I think that's a plus, times CA. And so what I could do is I could actually plug this in here. The problem does not actually ask us to do that. We could just say equal CA star, because we could just call this equation 2. So it's not a differential equation, but it does tell us a formula for CA star that could be plugged into the first equation in order to actually calculate the solution.